In this video, we're going to expand upon what we talked about in the video on bivariate contingency or crosstab tables. Let's start with a brief review of bivariate tables just to see how they differ from multivariate contingency tables. This data here is from the 2018 General Social Survey. We're focused on two questions in the survey. One asked respondents who they voted for in the presidential election of 2016, and the other asked people their race. I removed people who voted for third-party candidates and combined several of the racial categories in order to make the table easier to read. Just remember that the numbers in each cell represent a simple count of the people who were in both categories. For example, of the 1,361 respondents in the data set, 466 were both white and voted for Clinton. 298 were non-white and voted for Clinton. So from the table, it looks as if more whites went for Trump than blacks. But of course, we would have to percentage the table to check on this. Let's do that over here. Remember, we're trying to see whether our independent variable, race, helps us predict voting behavior, our dependent variable. So we place the independent variable in the column position and percentage down, as you can see here. We want the percentage of whites who went for Clinton, the percentage who went for Trump, etc. Here's the results of these calculations. If we percentage down, as I said, that is in groups of the independent variable, then we read the table across. So it looks as if there's a very strong relationship going on here. The percentage of non-whites voting for Clinton was twice the percentage of whites voting for her. And only a very small number of non-whites voted for Trump at all. So if I know you're non-white, it would be a pretty good guess, based on this table, to predict that you voted for Clinton. Fully 90% of non-whites made that choice. So again, it looks like there's a relationship. The question now becomes, is this relationship statistically significant? Of course, for categorical variables like these, we use chi-square to test statistical significance. To calculate the chi-square statistics, we need the observed count in each cell of the table and the counts we would expect, assuming that there's no relationship. The observed counts are in the table we started with. Here's that table reproduced. So to calculate the expected frequencies in each cell, we multiply the row marginal value by the column marginal value associated with the cell we're interested in, and divide that result by the total number of cases. So in the first cell, the one for whites who voted for Clinton, the row marginal is 764. The column marginal is 1029. So we multiply these two together and divide by the total, 1361, and this gives us 577.6. That's the expected number of people who voted for Clinton and were white, assuming that there is no relationship between race and voting choice. This table shows all the expected values. All right. So again, now it's just a simple matter of doing all the necessary calculations to compute the chi-square statistics. As the formula shows, we subtract each expected value from its corresponding observed value, square the differences, and divide by the expected value. We add these up for each pair in the table, and that's the value of chi-square. We'll use a summation table to do that, and here it is. The observed and expected columns were transferred from the table in the previous slide, and the rest is simple arithmetic. The chi-square value we computed here is 203.93. The next question is to see whether the chi-square value is statistically significant. For that, though, we first need to calculate the degrees of freedom that we're going to use to look up chi-square in our chi-square table. The degrees of freedom for this problem is 2. So where does this 2 come from? Well, degrees of freedom for chi-square is computed by multiplying the number of rows, minus 1, by the number of columns, minus 1. Finally, turning to the table in the back of your textbook, we find the degrees of freedom in the leftmost column and look across until we see the alpha level we're interested in. In this class, it will always be either 0.05 or 0.1, or I should say 0.01 actually. At any rate, the critical value for a chi-square in this problem is 5.991. The value we calculated is 203.93, which is much larger. So in this case, we would reject the null hypothesis that there's no relationship between race and voting in the 2016 presidential election. All right. So based on our chi-square test, it looks as if these differences, the differences in this table, again, I've reproduced it here for you, are statistically significant. But let's think about this for a bit. What else might be behind this relationship? What if these differences weren't due to race, but rather to some other variable that also varies with race? What about social class, for example? You can imagine that class might impact voting behavior if the non-whites were from the lower and working classes, and the whites were more likely to be from the middle and upper classes. That might be what is really driving the relationship that we're observing in this table. So let's take a quick look. In this table, it looks as if there are fewer whites in the lower categories. It might therefore be the case that it's not actually social class. It might actually be the case that it actually is social class and not race that predicts who respondents vote for. We can assess whether the relationship between race and voting we saw still holds if we control for social class. To do that, we set up an elaboration table. And here it is. We can think of each of these social class groupings as sub, or better, partial tables. Looking at them, it appears that the original relationship between race and voting was maintained. There are still large differences between how whites and non-whites voted, and regardless of social class, again, it looks as if most whites prefer Trump over Clinton. It does appear, however, that the difference, while still marked, is somewhat reduced among those who identify as upper class. Among lower and working class respondents, there was about a 50 percentage point difference between how whites and non-whites voted. But among upper class groups, the difference was only about 35%. Well, the next question is, are these differences statistically significant? Chi-square can only handle two variables at a time. So to test the statistical significance of these observations, you need to conduct 4 separate chi-square tests. One for the lower group, one for the working class group, etc. We're not going to go through that exercise here. I ran the test using SPSS, and as it turns out, the relationship is significant, or continues to be significant, except for the upper class respondents. Chi-square did not find that the differences in these cells were significant. I should point out, however, that the number of cases in the upper class group was probably too small for the test to be meaningful. So we would have to go back to the drawing board on that one. All right, let's take a look at another bivariate table. This one shows the relationship between satisfaction with college and participation in a student club. It appears as if students who did not participate in a club were less likely to be satisfied with their college experience than students who did participate. But what else might impact satisfaction with college? How about class standing? Let's again create an elaboration table to examine this relationship. Again, here we've created 2 partial tables, one for upper level and the other for lower level students. What happened? It looks like the bivariate relationship between participation in clubs has fallen apart. Among juniors and seniors, it doesn't appear to make any difference whether you're in a club or not. The same thing is true for freshmen and sophomores. Club membership made no difference. Looking at the table here, you would conclude that the relationship observed in the previous bivariate table was spurious. And that word spurious is important. A relationship that falls apart when we introduce another variable is a spurious relationship. All right, the table does show us something else, however. Can you see what it is? Regardless of club membership, the seniors were uniformly satisfied with their college experience. The freshmen and sophomores were uniformly dissatisfied. It looks as if class standing is what drives satisfaction. We can look at this table in a slightly different way to see that relationship a bit more clearly. In this table, all I've done is switched the club membership and class standing variables around in the columns. We now have two partial tables that hold club membership constant, and the numbers are the same, but the numbers are the same as in the last slide. This table just makes interpreting a little bit easier. From this table, it is very clear that regardless of club membership, what really drives satisfaction is class standing. Looking only at students who are not club members, it looks as if freshmen and sophomores are much less satisfied than juniors or seniors. And the same thing is true for students who join clubs. Freshmen are less satisfied overall than juniors and seniors. All right. How about race? Is the relationship we saw in the bivariate table sustained if we add race to the model? Again, take a look at this table. What do you see? For white students, the bivariate relationship we saw early on is maintained. Being in a club is associated with higher levels of satisfaction for white students, but not for black students. In fact, being in a club led to less satisfaction among blacks. This seems counterintuitive at first, unless, as it's been argued, black students are joining organizations that are critical of the college and therefore express less satisfaction. Well, whether or not you accept this explanation is up to you. The point, though, is that in this table, we see an interaction effect. Participating in a club does impact satisfaction, but how it impacts satisfaction differs for different groups. All right, so there are three possible outcomes when you introduce additional variables into a bivariate study. Either the initial relationship is sustained, this is what we saw in the election study, or the relationship can disappear. This is what happened when we introduced class standing into the study of the impact on club membership on satisfaction, or the initial relationship can be modified, and that's what happened when we added race to the model. So three possible outcomes when you introduce an additional variable into a bivariate relationship. Well, elaboration gives you the control for these other kinds of effects. And once you understand bivariate tables, expanding your analysis to 3 or possibly 4 variables is fairly straightforward. Elaboration, however, does have certain limits. The first one has to do with how you select additional variables. There is no hard and fast answer about what variables to select. You have to do this on the basis of theory and on the basis of your intuition and knowledge of your data set. If a subgroup in the data is overrepresented in one of the categories of your bivariate table, then it makes sense to look to see what happens if you look at each category of that subgroup to see whether its members respond differently. And that's just what we did in the college the college example. And also what we did, by the way, in the first elaboration table, we threw in social class to see if that made a difference, because we thought, again, that social class and race might be related. It's also important to remember that as we add variables to a bivariate table, the number of cases in each cell goes down, and this makes interpreting the table more difficult. Finally, reading a table with more than 3 variables, assuming you could even create one because you had enough counts in each cell, reading a table with more than 3 variables can be very difficult. The strength of crosstabs, though, is that they're easy to understand as long as you limit the number of variables and the number of levels or categories in each variable. If this is impossible, then there are other techniques to use. These other techniques can handle a virtually unlimited number of variables, but they are mathematically quite a bit more complicated. And for that reason, they're also harder to communicate the findings that you get out of them. We will be touching on one of these, however, later in the course. All right, well, I hope that you found this presentation useful, and onward.